go first a few minutes into intro to tabular foundation models, in particular the ones that are like TabPFN, the in-context learning ones. Then I'll talk about like some personal history of how we started messing around with tabular foundation models like this kind at Yandex Research, and what actually led us to some kind of productive research in this direction. Spoiler, it has something to do with the progress from the V1 to V2 models. And then I'll go through the core results from the paper. First, I'll discuss basically the status quo of how do tabular foundation models stack up against strong deep learning baselines, against strong classic machine learning baselines like gradient boosted decision trees. And also I'll share some of the analysis that we did in this work that I'm in particular really fond of, because this analysis kind of shed light into how the model internally operates. And I think it could help design better, more efficient and effective models in the future. And then I'll talk about the future, like what I'm doing now, what we are doing now, and speculate a bit about scaling. So yeah, feel free to interrupt at any point if you, for some reason, don't understand something in my introduction, or if you have additional questions regarding research directions in the later part of the talk, yeah, feel free to interrupt. And then, okay, yeah, let's go start with a bit of history. I guess everyone is familiar these days with the concept of in-context learning. For me, it's kind of the moment where it erupted, all erupted, was the GPT-3 paper, which showed that sufficiently large, sufficiently long pre-trained models exhibit some kind of in-context learning. For example, when you specify the desired task in a textual format, for example, like this slide has a translation example, and you give a few examples, the model could just continue to produce the similarly looking examples, and it basically learns a new task in context. This plot shows from the GPT-3 paper that on many tasks, the few-shot performance is actually improving with model size. But what we actually need to understand at this point is that it's a kind of a paradigm where the model somehow learns from the data set that we can supply in context. So what does this do with tabular data, you say? We need a small aside into this paper called Transformers Can Do Bayesian Inference. It was the precursor to the actual TabPFN work done by the same authors in Frank Hatter's lab. So they basically propose a formalism in using the Bayesian framework of the in-context learning. It's a crude understanding, but it helps, I think, to understand how those models operate. So what does this framework looks like? We basically have some sampler over datasets. In case of the GPT-3 paper, our sampler was just looking at the internet texts and sampling sentences and paragraphs and etc. from the internet. In case of, for example, images, it could also look similarly. We basically have an infinite amount of different tasks somehow sampled. It's represented by the X test and Y test, where Y is some kind of label. We can imagine labeled supervised classification or regression example. Then we just train the model to produce the correct labels given the test sample features and given the in-context dataset that we sampled earlier from some kind of a distribution. So we basically learn the in-context predictor. It's parameterized by the transformer in this paper, and they basically show that it approximates the Bayesian inference in this case for the training set, albeit informally, if I'm not mistaken. So yeah, this is a procedure to learn generic in-context learners. A simple a note on architecture. We use a simple transformer here. We encode the pairs of inputs and outputs as singular tokens. We allow the attention to look to basically be bidirectional when processing the training set, and we disallow the attention between individual test examples during the forward pass, but we allow the attention from individual test examples to the whole training set. This basically resembles, like, for example, language modeling with the prefix language model mask, or it's basically the closest description of like known things to people, or basically it's something like an encoder model with shared weights with the decoder that just produces the label. So yeah, it was the model architecture. They showed that such prior fitted networks, so we sampled data from some prior, and we learn a neural network that just fits something like and makes prediction in one forward pass. They enable like super fast prediction because it's just a forward pass of a small-ish transformer. So it resulted in like huge speedups compared to like existing state-of-the-art in Bayesian methods. Here is a simple example before we go to the tabular one. It's from another paper from the group that like analyzes and talks about the properties of generic prior fitted networks. So here we can see that we can have like a data set of just regression with a singular feature. And we can sample from, for example, cosine function and from linear functions with different slopes and different cosine parameters. And this is our data. And the model learns to, for example, infer from the black points. It can infer, oh, wait a second. It can infer the desired relationship between the input and the target. And it could also generalize, like combine the sine component with a linear one. So yeah, it's a toy example, but a nice one of showing that the model basically somehow generalizes and produces coherent predictions. But how do we sample from a prior distribution over tabular datasets? This is the core question behind the TAP-PFN line of work, which I'll gonna refer to in the latter part of the talk. The problem is that we can't, we actually can go look for tabular datasets in the internet. We even will get a benchmark that's called Git tables, I believe. The Git is not a coincidence, because like most of the tables are on GitHub in like CSV files, or even in Jupyter notebooks, like headers, for example, when you try to do like explorative data analysis and you do like pandas data frame head, and the respective dataset sizes are kind of small in this dataset, this collection from the real tabular dataset in the internet. And it's lacking in terms of like real world use cases and real data, like real sample sizes, which we can encounter in like tabular competitions. You can go a second option, and you can go look for like Kaggle datasets or competition datasets, but they are like too limited. The licenses are limited. So the authors of TAP-PFN proposed a different way to do this. And in my personal opinion, this is one of the things that like attracted basically half of the tabular research community to this topic, to tabular foundation models based on in-context learning. It's the pre-training on synthetic data. Now I'll try to explain how this synthetic data is sampled. So let's have a concrete example. We want to sample one tabular dataset. We have nothing. We have like no models, no data to pre-train on. In this example and in training tabular prior fitted networks, we do with just PyTorch random number generators. For generating a tabular dataset, we first sample a causal graph. You can imagine it as a very sparse neural network also. It would be useful in a bit. This causal graph just demonstrates the dependencies between some kind of variables. The connections in this graph can be like arbitrary activation functions. They can be even arbitrary functions. For example, it could be represented as a neural network or as a decision tree or like basically anything else. We can model connections anyhow we want. Then we assign which of the nodes in this sampled causal graph would be the input features, in this case x1 and x2, and which node would be the target. It could be that features depend on a target, and target depends on some unobserved variable that is the input in this causal graph. And then we just pass through the some number of random inputs, randomly generated vectors through this graph and observe the dataset basically. And then we can just say that one partition of the dataset is a train set, and then leave like 10% for the test set, and just train the prior fitted network as in this slide, like in this framework. And we basically have infinite amount of datasets. The question is, are they any useful to like actual tabular data prediction? The first version of the paper showed strong performance on small tabular datasets. Small datasets are datasets with less than 1,000 samples, and oftentimes much less, like in first hundreds of samples. And the main selling point at this point was that it's performing in under a second on a GPU, and it beats the gradient boosting tree or automatic machine learning baselines, which require some hyperparameter tuning. At this point, we were like really interested in this line of work. It was like 2021, 22, around this time, because, like as I said, it showed non-random at much better than random performance by being pertained on synthetic data sets. And it was also like near the boom of context learning, and it was easy to like generate new ideas around the general framework. But there were also problems because the dataset size was really limited by like 1,000 examples. Same goes to the features, same goes to not supporting the regression task, which is regression, like many tabular problems are regression problems. So yeah, it was like an initially interesting research, and it shows like in the citations of the original work, and actually the lab and people behind the original TAP-PFN model raised some money and are doing their startup now, which is focused on making new tabular foundation models, and TAP-PFN v2 is actually part of the startup offering. There are like workshop dedicated to foundation models. Half of the workshop is about tabular foundation models specifically, and this kind of tabular foundation models is at the moment the only one that actually works and somewhat is useful in the scenario of like supervised classification on small to medium scale datasets. So yeah, it was a nice thing, nice research direction. But how did we get there? Like, why did we start working on tabular foundation model so late? And what actually got us to work there? One interesting story is that we actually did try to work on tabular foundation models in around the TAP-PFN v1 model. We tried to train like the model that would support regression, that would we try to like naively scale this approach like on the synthetic data. We got the results from the V1 model like reproduced. We got some regression working, but we had like our internal understanding and internal benchmarks because we did lots of research on like classical deep learning models where you fit a model on a target data sets. We have like data sets that are much bigger than 1,000 samples. And in this case, the first variation of the model didn't perform like our own reimplementation and the original model. It didn't show results better than the, for example, multi-layer perceptron, the default one with just moderate hyperparameter tuning. And it was like much more cumbersome in terms of like running a transformer, going and in and putting all the data like from the training set in context. It wasn't like paying off in terms of metrics. The complexity wasn't paying off. And so we just froze in this direction until the TAP-PFN v2 paper came along in 2025 from the same authors of TAP-PFN v1. And then we tried it. First, we tried it on our datasets, which were like much larger than 1,000 samples. We got the state-of-the-art results from in-context learning on some datasets. It's a joke on like we have overused basically the California housing example from sklearn to do some kind of initial experimentation. So if you have questions about the specifics of the California housing datasets, you can ask ourselves. So we know it's like everything about it, and it's a really good score on the California housing datasets. So yeah, we were initially very excited and tried to do something with it, like evaluate it on a larger number of datasets, because like on California housing, you can basically get to around 0.4 with just a KNN regressor, a bit modified in terms of weighting. So yeah, it's a simple dataset, like a kind of tabular MNIST for us. So we wanted to include more datasets and have a broader evaluation. So here comes our initial status quo kind of evaluation of where TAP-PFN lands. The actual TAP-PFN paper also has the evaluation. It shows that TAP-PFN v2 is better than, for example, XGBoost baseline when properly tuned. Like TAP-PFN also has some parameters in knobs to tune, for example, like input feature preprocessing or something like that. We were interested in a bit of a different niche. We were interested in larger datasets. TAP-PFN explicitly mentions that the model is limited to 10,000 objects in datasets and like 100 features. But in principle, nothing stops you from using the model on any dataset, like of any size. It actually generalizes really well on datasets that are much larger than the pre-training corpus size. So this is like the one point. Second point, we had our like internal pipelines for tuning models, and we also had state-of-the-art deep learning baselines. For example, the TABM model, which is currently really popular in terms of in Kaggle competitions, and it actually is a proud member of many winning competition ensembles nowadays. So it was like our initial interest to compare to strong deep learning baselines, which are actually stronger than the classic machine learning XGBoost, for example. And also we tried to like push the limits in terms of number of samples and the sizes of datasets. What can we see here is the plot that shows an average improvement over the MLP model baseline. It's basically an okay model that works kinda, but is not state of the art. We can see that XGBoost, for example, averages at about like 2% improvement over the MLP. Some earlier tabular deep learning, classic tabular deep learning models in like MLP, which is denoted MLP PLR, is a bit behind the XGBoost model. We also can look at the average ranking that takes into account the like statistical significance in result differences. And for example, TabM is beating the XGBoost model, especially when like ensembled at around 3% improvement, and like clearly beating in terms of rankings. And when we look at the single TabPFN model, which was also of interest because like the original TabPFN paper uses the transformer, which I described, like the in-context transformer, in some kind of automatic machine learning assembly way. Like it uses many models with different parameters for like each instantiation of the model. They can use like different preprocessings. In like we are especially in our research group at Yandex Research interested in like foundational abilities, like what is this single approach when like compared with similar preprocessings, similar circumstances. How does it stack up to another models? And it's actually, in my opinion, it's like getting to the personal opinion here. It's actually simpler to use. Like when you have one part of the system, not like a complicated one, you can understand it, you can more easily deploy it. So we strive for simplicity here. And when we looked for a single model, like it's denoted no fine tuning here, no FT. More on that later. It's actually below the XGBoost model in terms of average improvement, but it's around the same in terms of statistical significant rankings. And when we use the ensembled variation, it is also a bit behind, but it's like closer to the deep learning baselines of the 2022, 2023, which is really interesting because like to get to the MLP PLR, it took us a lot of research and it took us like some time to get to this XGBoost level performance in terms of ranking. So when we get the default TabPFN ensemble that performs on the same level, it's definitely interesting and worth taking a look at like further. But we can see clearly that, for example, TabM model in this comparison is clearly better on those kind of datasets. Here we use datasets from the paper of why tree-based models outperform deep learning baselines. It's an interesting paper to use in deep learning model evaluation when deep learning models actually outperform decision trees. But yeah, this is like a set of 17 datasets, if I'm not mistaken, that we've selected. So yeah, it was our next move and question was, can we basically improve this? Like in context learning performance when ensembled is decent, but it's not state of the art. Can tabular foundation models be state of the art in terms of performance on tabular data in this niche of identically distributed data sets with around tens of thousands of objects? So we just fine-tuned the model. It's an immediate first step when you have a dataset which is large enough and you have a model that performs somehow. You basically fine-tune it. People in deep learning were doing this like years and years ago. Like in computer vision, it's the usual method that you get some kind of pre-trained ResNet and you fine-tune it to your condition and dataset, and it's like miles better than using the model which wasn't pre-trained. Like using pre-trained models and fine-tuning is actually the way in other deep learning disciplines. In tabular data, it wasn't available for us. We just trained the models on each dataset individually. With TabPFN, you can fine-tune it. It performed decently without fine-tuning, as we can see. But then first is the question of how do you fine-tune it? There is actually a nice blog post from Thinking Machines circulating on Twitter right now about low-rank adapters being the same as similar to fine-tuning in terms of final performance. The blog post talks about reinforcement learning fine-tuning for language models. We are talking about tabular foundation models. And here the situation is similar, but the motivation is different. There were a lot of papers after the initial TabPFN V1 model that proposed kind of complicated pipelines for adapting the model to target tasks, for example, via fine-tuning or via some kind of subset selection for the in-context learning part. So in some papers argued that LoRa and low rank adaptation should work best because it has like some regularizing properties. Some papers just used full fine-tuning without the ablation. Some papers fine-tuned the embedding module. There was like everything was all over the place, and like basically there was no consensus of how to do this. Some people just do LoRa fine-tuning because like everybody does LoRa fine-tuning on transformers nowadays, and it's like the meta. But TAP-PFN model is actually very small. It's like 20 million parameter transformer. So the efficiency part of LoRa is out of the question. So you don't need to save on compute in terms of like model in memory. And then we showed that basically each and every reasonable fine-tune is okay. For example, like full fine-tuning only the last layers, LoRa fine-tuning the embeddings and layer norm parameters and the head parameters, or introducing some kind of other input modules which are more advanced and tailored for like tabular features, and fine-tuning this way, like everything performs the same. It's basically and we argue that you should basically use full fine-tuning because it's like simpler in terms of implementation, and it also converges much faster. It converges to the same result, but faster, and it's just the simplest baseline to try. And the second thing that we can look at here is the comparison now looks much different when we compare to the fine-tuned models, which are adapted to the dataset. For example, like when we fine-tune the TAP-PFN model on the target datasets, on each dataset, it starts outperforming all other models, like even the ensemble of the TAB-M models, and it outperforms it like significantly. And it can also be improved in terms of like ensembling. So yeah, tabular foundation models are very strong after fine-tuning, but there are some caveats. First caveat is this is not the case on some more challenging data distributions. In Yandex research, we have a benchmark called TabRed, which represents real world, like industrial use cases you basically encounter in applying tabular models in production, for example, to weather prediction services, or in navigation systems, or in services like food delivery, like Foodora, or something like that. You have lots of objects there, but here we are limited because of on large dataset, it's really tough to fit the entire large dataset into transformer model context. So we experiment on smaller subsamples of the TabRed dataset. Another thing is there are all kinds of distribution shifts. There are all kinds of missing values in the features. The actual datasets are much harder, like informally. It's a much harder task to perform well on TabRed. Like many methods that are close to state of the art on like California housing like datasets and sklearn are not close to like gradient boosting or proper state of the art deep learning models. So TabRed is like a great filter for approaches that would transfer to this like harsh reality of the machine learning in production. So in here we see that TAP-PFN without fine-tuning is like behind the TAB-M model, and much more behind in terms of like average improvement to MLP. It is often behind the MLP baseline, like on the data sets that are circled with yellow, it's below the MLP baseline levels. And on some data sets, it even like fine-tuning doesn't help. We show like later in the paper that it's basically because of some kind of overfitting, because those dataset when subsampled are very small, and you can do basically nothing when fine-tuning. And there is also a distribution shift between the training and testing, and fine-tuning also can break down a bit in this situation. So yeah, first problem is you can fit big datasets, and actually it is not really the case that TAP-PFN performs and is state of the art like in each and every situation. Your situation may be like this, and some situations are not like this. For example, like production like ML, which is also similar to most tabular Kaggle competitions, which also have like lots of features, lots of data, and also often come from like production use cases. So here, TabPFN is kind of questionable in terms of performance for now. And also, what we can see in transition to the next point is on these benchmarks, another model which I omitted previously, but which is really interesting in terms of tabular deep learning models, is modern NCA. It's the model which uses a neural network to learn an embedding space in which we perform the basically soft k-nearest neighbor regression or classification. It's a very simple model, just learn an embedding space with an MLP and just average out all the training labels to get a prediction. So such kind of models like modern NCA or, for example, Tabular, we developed at Yandex Research, they often perform worse than the MLP baseline on Taburet. The reason behind this is like to be discovered and disclosed in the future, but it's actually the case, and it is the case for TabPFN. So the next part is about the analysis we did in the paper. It actually helps shed light into how this black box foundation model, like that does in context learning, actually does it. And I think it could help us like understand and design better models when we get through this understanding. So yeah, this is basically modern NCA. We have an L2 distance between like an embedded objects, and then our prediction is like just soft combination of all the training set labels. And it actually is quite performant in terms of like tabular benchmarks. Here it's again an academic benchmark where it outperforms like all the gradient boosting decision tree libraries, and it's behind just only the TabE model. So yeah, it's kind of when you plot, for example, the improvements or like error characteristics of the modern NCA model and the TabPFN model on this benchmark, even the academic one, you can see a greater correlation between these improvements. Like there is some hints that in context learning may perform something similar. Like the one obvious hint is that we just put the entire labels of the training set into context. So the model in principle can do this. Like it's one of the strategies it can use to do a prediction. And this strategy actually works with modern NCA. So this is not some kind of wizardry or something really unusual. We just try to look at this a bit more closely. So what we did, we took the attention scores from the last layer of the TabPFN model, which has the tokens for each feature and also has a special token for the targets that are encoded from the training set. So we basically look at the attention from the test example to all the training targets in the dataset that we supply in context. And we just use those attention scores to weight around, like in this formula, to just weight the raw targets from the training set. We basically perform soft k-nearest neighbors classification, but with scores from TabPFN. There is also a paper on the ACL workshop this year, which does this kind of stuff explicitly to learn like a more explainable and understandable TabPFN. So, and we can see that the attention scores of TabPFN, when you look at the weighted KNN performance, are actually decent. Like they are okay. This soft KNN classification and regression kind of works. But what is really important for us here is does fine-tuning on a specific dataset change something here? And we can see that a fine-tuned model, the model that is fine-tuned on, like for example, California housing dataset, is improved when used like properly. But the KNN weighted performance also improves, even quite markedly in some cases. So here we see that this mechanism of weighting in the targets of the original dataset is kind of important in terms of TAP-PFN prediction. It's not all the way there, like there is some kind of other processing happening in the model, and it's like an interesting research question, to explain the difference between the weighted KNN and the actual TAP-PFN. But what we're interested here is like there is something here in this attention, in this attention distribution, in this attention scores, and it model definitely looks at the labels in the training set and performs some kind of retrieval inside. Here we dive a bit deeper into this, and we look at how first we look at how the distribution of the attention scores changes from the in-context model to the fully fine-tuned model. And on many datasets like California on Diamond or Adult, we can see that the entropy, normalized entropy of the attention actually decreases for most examples. Like the attention becomes more concentrated. But on some datasets like House or, for example, Paul or Churn, this is not the case. Like it reshuffles somehow, like the model starts to look at different examples for different test instances, but there is no like clear decrease in attention entropy here. But what we are interested then is the plot below, is how the actual performance improvement on each individual sample is correlated and how it's related to the change in entropy. Is it basically the case that we get the most improvement when we decreased, when the entropy of the attention distribution, looking at the test instances, decreased the most? And this basically is the case for most of the datasets. Like it's clearly seen on the adult dataset like House and Paul, less clearly, but also distinguishable at the left end of the plot on Diamond and California. Like the largest improvement from fine-tuning comes from the regions where the entropy decreased the most. So yeah, this hints that like even fine-tuning performs a procedure that somehow refines the retrieval ability of the model. So model starts to look at the relevant examples more, and it doesn't look basically at anything else. It's becoming like sparser, you can say, when the entropy decreases. So yeah, this is the part of the analysis that I think is important, like the correlation between tabular foundation in context models and basically retrieval models, and that the fine-tuning actually is like a very related to here. Fine-tuning does improve tabular foundation model in context performance very much, and it improves it in the regions where we started to look at different objects after fine-tuning. So it basically kind of improves the retrieval performance, one can say. So I'm finished on the part about the paper, and now I want to talk about like some speculations and related work that came after our paper. If you have like some questions, I can stop for a bit.
I think there's one question from Elias. Maybe I will just quickly unmute you and you can ask your question. You should be able to unmute you now.
Yeah, I think I'm unmuted now.
Yep.
So I was wondering about the retrieval in your analysis. Do you only look at the last layer of that PFN, or do you look at all the layers?
We initially looked at all the layers and actually all the tokens. We found that only the last layer and only the token that corresponds to the white train, to basically the training label, is informative. Like all other attention layers perform some kind of like message pathing thing that is not informative in terms of like target closeness in train set to the test set. I can speculate that when you take into account like for example, all the attention maps in the model. Like when you try to, there are some methods that try to like incorporate attention maps from all the heads and all the layers correctly to like weight which examples in the context of the model are more important. If you do this kind of trick, it may be better in terms of like weighted KNN performance. But what we actually found, like the most important and informative part is at the end of the model, like the 12th layer, and only the token that corresponds to the target.
Because yeah, I would expect that it would also do some retrieval in the not only in the last.
Yeah, sure. Yeah. It's like a very, very loose analogy. I believe it does something like in the intermediate layers. It should do something. It's an, as I said, like an interesting exploration direction for a future, because the models
All right,
are
thank
like
you.
really small. And yeah, thank you for the question.
Yes.
So yeah, let's go ahead and speculate a bit and talk about more of related work on tabular foundation models, some of which is from Yandex research. Here, I would first talk about like our efforts at scaling up the results even further. As I said, like the initial problem with TAPFN v1 was the limitation in terms of like number of samples. Same goes for the second version of the model. Now the limit is like at tens of thousands of examples because like it's where you comfortably can train on like one GPU or one host of like moderately sized GPUs. And then when you try to go beyond that, which is a very admirable portion of actual tabular datasets. Many tabular datasets have like more than 50,000 examples. So then you encounter problems. For example, when I did some kind of, so what I did, you can basically run TAPFN on arbitrary sized datasets, which was shown in this paper. I guess this paper main argument is that you can just run TAPFN on larger datasets and it will work out of the box. It's also not surprising because TAPFN doesn't have any kind of special positional embeddings that you need to adjust. And when you think about like tabular foundation not tabular, but language model foundation models, there are lots of like research where basically the one important thing is to somehow to adjust the positional embedding and to do a light fine tuning to enable some kind of lens generalization. So in TAPFN, you don't actually need to do all this stuff in terms of like adjusting numerical embeddings, and it actually works out of the box. Here we can see that like custom TAPFN is the model that just is evaluated on larger datasets on the recent TabArena benchmark. It actually performs quite well, even comparably to the TabICL model, which is explicitly in terms of like architectural details tailored to perform better on larger datasets and pre-trained on larger datasets, like random ones. And it actually is better than imputing TAPFN performance with like random forest baselines. So yeah, it is actually feasible. And I did this in my initial experiments on some datasets like full tabret datasets and like larger datasets that reach up to like 700,000 examples. But there were some problems. First problem is the double quadratic attention. So you have like a dataset with m features and n samples. So your attention computational complexity is actually mn squared plus nm squared. So it's double quadratic in terms of if you have like many features and you have many samples, you have a batch of many feature attention and a batch of many sample attentions to do. And here we basically compute the attention operations, and it nicely corresponds to the actual like runtime during model fine-tuning. And as we've seen before, fine-tuning is actually crucial to achieving state-of-the-art performance. And when we go beyond that, when we go like to real-world dataset sizes in like millions of samples, it becomes quickly becomes infeasible and requires like more engineering and like ideas. The other problem was the actual performance. It was not good, not even competitive with the MLP baseline, which uses all the samples from the dataset to train on. This is actually an unfair comparison to TAP-PFN because it was trained on datasets with up to 1,000 samples, like and random ones, random datasets. But it is actually interesting to like probe its capabilities at the like basically at the edge, like on larger and larger datasets, and like on to evaluate the TAP-PFN in context learning performance on Microsoft datasets, for example, it took around like 20 hours of just straight attention computations on single GPU. So it's not practical, but really interesting in terms of pushing the performance forward. For me personally, it's interesting because like TAP-PFN V2 model represent an alternative retrieval paradigm, because like earlier tabular retrieval models, which were really state-of-the-art on academic benchmarks like modern NCA and Tabular, they all perform like single vector retrieval. They just encode each sample and they select the closest one. TAP-PFN actually is akin to the, how do you say it, like cross encoders in terms of like information retrieval. It uses a whole transformer model to compute similarities. So it basically can encode much more fine-grained and hard similarities. So it can be a way forward for tabular retrieval models, but it's still a long way for this to happen. Yeah, basically there are still questions like, will fine-tuning help on these datasets? If we make it feasible, it may help. It's an interesting question for me. In some initial experiments, I've seen like fine-tuning bring TAP-PFN where it was feasible, like with checkpointing, with like all sorts of tricks to manage memory correctly. It was on like nice state-of-the-art level performance levels, but it was basically comparable to the TABE model. For me, the wonderful and interesting result in terms of applying tabular foundation models further would be if it beats, for example, current state of the art as it was on early academic benchmarks, as we've seen, like with fine-tuning. If this happens, then we will definitely live in the future where like tabular foundation models rule in terms of being applied everywhere. So yeah, basically, where is the limit of this pre-trained fine-tuned paradigm with tabular in context models? Basically, should we just train on the large enough data set? Like when does synthetic pre-training stop being relevant? Does it actually stop being relevant? That's the question that is like needs an answer from, in my opinion. So yeah, there are papers from even like 2024 and recent ones on using real data to improve like tabular foundation models. One paper from layer 6 AI, it's TabGPT. It actually argues that tabular foundation models, the ones based on in-context learning, actually scale better when you use real data. It like argues basically for using real data and as much as we can. The second one actually does a continued pre-training on real datasets, and it shows that it also like provides substantial performance gains on benchmarks. So yeah, maybe using real data is the way. I guess we should answer better to this. Another encouraging sign about tabular foundation models is that these models are basically the only models that are good graph foundation models. So a bit of a precursor, there is a whole part of machine learning that deals with graph data, like graph machine learning. And it historically struggled with benchmarks because like in many real world scenarios where you want to use a GNN, you have some kind of complex object representation, complex objects and real world important tasks. But actual benchmarks that were used in academia were all about citation networks and using bag of words features as features. So the GNN like community developed with kind of flawed benchmarks. So Yandex introduced the Graphland benchmark, which has all sorts of real-world tasks like click-through rate prediction, like recommendation, or tasks on a large city road graph, for example, predicting traffic jams. And it has like complex objects of having various features and also tabular features. So, and what they do here, and they test classical GNN baselines on such datasets. They also test all models that they were able to get working, all the foundation models from the graph learning community. And it basically shows, when we look at the average rank, that like a simple light GBM with feature aggregation using the provided graph actually outperforms most GNNs and outperforms markedly the graph foundation models. But when you lightly adopt when you just pass the graph features into TabPFN or the latter Limix model, which was released from Tsinghua and some startup like earlier this month, when you do this, and when you do in context learning on graph data, it basically outperforms GNNs, and it basically outperforms the when you also stack fine-tuning on top, like I said in the earlier part of the talk, it basically becomes state of the art. And the Limix model shows that there is like untapped potential in the pre-training. It just shuffles, it just introduces minor changes into the pre-training of TabPFN, uses a very similar architecture, and you can see a difference between the TabPFN v2 and Limix. And Limix fine-tune is like the clear #1 model on even on a graph benchmark. So it's an encouraging sign, because it's an unseen benchmark from a different domain, which was constructed like without TabPFN in mind, and TabPFN couldn't have used it like anyhow during training. So yeah, it's a good sign for the future of tabular foundation models, at least in some kind of domain, even if they don't scale. Another like last note here is a great paper from the lab that introduced TabPFN, is drift resilient TabPFN. For me, it shows that the paradigm of pre-training on synthetic data could actually be useful, like in general, because this paper introduces a simple trick to basically control the data generating process, to introduce some features that we need the model to take into account. Here, like tabular datasets all very often exhibit some kind of temporal shift. For example, features change, feature distributions change, like demand on like taxi services change, and your demand prediction model also changes. You have to retrain it, or some way of adapting it to the real world. So, and here they progressively with the time step introduce changes into the causal graph, which is used to sample the features for synthetic datasets. And then they show that when you train a TabPFN on this specifically controlled setup for generation, it starts to basically adapt to data distribution shifts. I guess we can think of many things that we can control in such way in the future. Yeah, if there is any questions. Oh, yeah, got to go. And we are actually at the end. One more thing is our most recent paper, which may be of interest to Cornelius, for example, because we are talking about LLMs and tabular data intersections, but it's for another talk, I guess. We tried to make a more interpretable and faster and simpler model with the help of recent LLMs, which can actually code quite nicely. So we do an agentic loop that analyzes the dataset and produces a better single decision tree for tabular classification. Yeah, maybe next time we'll talk about this. So yeah, if you have any questions, if you haven't already joined our channel and our community on Alpha Hive, also you can follow me on Twitter. You can read the paper at this QR code, and you can look at the code for TabPFN fine-tuning. I specifically suggest looking at the code because I plan to like make improvements and like, for example, introduce limits there, try to introduce the scaling experiment there. So yeah, I'm not finished here. Yeah, thanks everyone. If you have any questions or suggestions.
Amazing. First of all, thank you very much. There's one question
you.
in the chat. From what source was the table on graph benchmarks?
Oh yeah, sorry, it was an accident. It was from the Graphland benchmark paper. Oh no, it was from this basically paper, graph to tabular foundation model. So yeah, you can go ahead, look into this repo. It has all the relevant links to the paper and to the graph benchmark. At the moment, the Graphland benchmark is awaiting the PR into PyTorch geometric. So if you are doing like some graph learning, you can go ahead and like the pull request there. So it goes in quicker and use it in your own research, yeah, if you're interested.
Awesome. Are there any other questions? Otherwise, I have a few. Maybe I can just start.
Yeah, sure.
Start with those. And if anybody else has a question, feel free to just reach out in the chat. First of all, in the beginning, thank you for the amazing talk. Like that is super interesting to me personally as well. So I was super curious to hear about your latest paper, but also especially on the like vision where things could go next. I have a question from the beginning though, because you said that you specifically looked at these larger data sets and you also like dived into, okay, does the context scale well, like, because like you said, there's no positional encoding, so mathematically there's no limit to how much you can put into the context window. But what about smaller data sets? And I think there are two components of that to that question. First of all, doing fine-tuning on a technical level, did you see like in the beginning maybe some effects like catastrophic forgetting, and like what was the behavior from these different fine-tuning methods when it came to smaller data sets? Maybe you have some insight. And the second is maybe answer that first.
Yeah, I can start. We have actually seen something mildly interesting on smaller-ish data sets. There were like this result on this subsample of this Beerbank housing dataset, where we have a no fine-tuning, averaging like minus 20% over MLP. And then when we do fine-tuning, it goes even worse than that. And there was even another dataset, which is not on this plot, but it is like the lowest one here in this plot. It basically even maybe not shown, but like the one below 0 for the full fine-tuning, like the dot. And it's also one of the smaller data sets from the academic benchmark. Another factor that is similar for these two data sets is that their relative number of features to samples is quite large. Like they have very many features, and like the overfitting is severe on these datasets. And like this one also has temporal shift. So in this kind of scenario, I believe there are problems with forgetting or even like overfitting to the smaller dataset. But on these small datasets, I personally believe that like future incarnation of foundation models would be like better and better and better, and fine-tuning would be less and less of a priority. So I guess the the game with fine-tuning and where do we need to fine-tune is on a bit of a larger data sets that I personally think. And maybe like some methodological things like LoRa actually, like low rank fine-tuning actually kind of helps when datasets are smaller. Maybe true, but generally when like datasets are not super small, it's okay with full fine-tuning. So yeah, to summarize, there is some effect there, and maybe we can control for it. But I personally believe that like future foundation models and even today's ones are good enough, but it may be my oversight because I'm like too focused on a larger data set because of where I am.
Yeah, but that ties like neatly into my gut feeling of that LoRa helps here, because that's what we've also seen with large language models, that LoRa's help with like limited data availability. But also you made a very nice transition to like these models are great at like with smaller data sets. I mean, that's what you also said, like TabPFN was initially focused on. So, but as a like larger research field, where do you think the focus should be in the future? Should we focus on improving foundation models on these very large data sets, or should we like also focus on these smaller data sets that we couldn't like very much classify with MLPs because we just didn't have enough samples? Like, where do you see the balance in terms of research focus?
Yeah, great question. For sure, I think that like from my point of view, and like it's not the ground truth 100%. Like it's just one singular point. I think many people are focused on like scaling this up because it proves like a challenge and from possibly an interesting question. I do think that focusing on smaller data sets is actually important and a bit kind of overlooked when talking about like extensions and talking about TabPFN. There are like lots of applications, I think, in science, in like interpretability and stuff. Like if you have a very good predictor, which was like, as you said, you weren't able to fit an MLP on such small data set, but you can obtain a very good predictor with TabPFN, and you actually can look inside and understand how it operates with your data. It can actually probably provide you with some insights about your data if you are like in sciences. But yeah, for me, the other end, like with scaling up, I think we should think about it more, like more foundationally, because what I see now is like each and everyone tries to retrain their own PFN, like with the Limix, for example. Like it's a really great work. Like I really love this showed that there is basically more and more like potential in doing this kind of thing with synthetic pre-training within context learning models. But it's basically what I said, like doing the kind of same thing and switching and triggering like small pieces in and out. Like the field is first of all greatly misses like ablation studies because we really don't understand what is important. Like, do we need even such transformers of such size? Like, is 20 million small or big? Do we need synthetic data? What is the limit? Like, these are all questions that we should focus on. And then secondly, like if it is actually performing some kind of retrieval, maybe we can do this more efficiently. Maybe we can do something that is more specific to tabular data, not using just the transformer. So yeah, I guess efforts in both sides are appreciated. Maybe smaller data sets or some kind of multimodality work is more overlooked, and in my opinion is where this thing will actually be needed. Like for sure, 100%. This is the niche where tabular foundation models like TabPFN are very useful now and will be like all the time. And the scaling up question is question still. So this is my answer. Thanks for the question.
And if there's nobody else, I will have one final question, but I'm also happy to give the floor to anyone else who has questions. But okay, that doesn't look like it. It's actually exactly on the slide which you are currently on, and it's
this one.
But no, yeah, this one. No, the one with the yep, exactly. And it's a bit of like detailed question, but you use the like MLP performance as a baseline, which I appreciate a lot because that's what people use traditionally for these tasks. But still, I wonder like what was the overall performance of these models on these tasks in terms of accuracy? I'm just asking because if you like an improvement from 92% to 98% would be, in my opinion, much more impressive than an improvement from 60 to 66%, because like the final 10% are like in classic notions like the hardest.
Yeah,
like what was the overall performance?
Yeah, that's a good question. That's actually this plot is brought into the world of thinking deeply about this question exactly. Because, like, for example, how do you choose the baseline to compare to show this like percentage improvements? If it's too weak, like for example, many papers choose to use like KNN or even simpler models. They can achieve like more spectacular plots in terms of relative improvement, but it's less impressive in real life. So yeah, the answer is like MLP is the best thing we can get for this kind of job in terms of like comparisons, because the actual the metric values vary very widely, because like in this plot there are like half of the datasets are regression, half of the datasets are classification. There are classification tasks that are close to being solved, like more than 90% accuracy. There are regression tasks that are similar, with like R-square metric close to 1. And there are basically tasks that are nowhere close, with like lots of randomness and much lower percentages, but the actual MLP model is always close behind the like more advanced models. For example, like if you have a TabM model, it's better than the MLP for sure, but it's not like the soul-crushingly better. Like it's all like around the similar kind of levels. That's why you can see like it's around 2% of improvement like on average. So yeah, it may look more moderate than in some other plots